All right, we have another unit review video. We are on Unit 3. So we did Scientific Foundations, Biological Psychology. This is Sensation and Perception. And that leaves 4 more until the AP test. I'm pretty much going to be going down the terms. I don't really know what else to do, and then using that as a catalyst to talk about things. Like the other unit review videos, this will be very shortened. This will be a review, not learning the first time. Also, you can see I wore my Light My Path McGinnis shirt, and the Light My Path is in green, so you can see through it. That was kind of funny. Anyway, so let's get started. If you can go to the website here /SP, that'll bring you to this page, and that has the Quizlet and the terms. We're going to use the blank terms. There are sensation and perception is sensation, which is your sensory information coming in, it's the raw data, and then perception is what your brain does to interpret that raw sensory data. There are 2 types of processing, bottom-up processing or top-down processing. Bottom-up, top-down is best illustrated by the backmasking videos where you can listen to a song forward with the lyrics.
If there's a bustle in your hedgerow, don't be alone there.
And so forth. But if you listen to it backwards without the supposed lyrics, that would be bottom-up processing. So that's the raw, it's what we just listened to backwards. That's the raw information. So it's this. Sounds like nothing. But if I give you the top-down prompt, then it affects the way you perceive this sensory information. So with the lyrics now, you hear this very differently, and now you can read it almost perfectly. And that's with the 1970s supposed playing the music backwards thing that happened. But just listen to it backwards would be bottom-up processing. Listen to it backwards with the lyrics would be top-down processing, since you have context clues, which greatly influence how you perceive that sound. Selective attention, we can only pay attention to a relatively small amount of things at once. Like even when I'm talking, there's a lot of things going on the screen which you're not paying attention to. You only, like the tabs I have open, the time it is right now, what day it is, all my icons and everything, everything. There's 1,000 things, what your chair feels like that you're sitting on right now, but you only can pay attention to a relatively small amount of things at once. And then inattention blindness is you become blind to the things that you don't pay attention to. So every time, it's hard to point to stuff, but in the bottom right corner there, the time, every time the minute ticks to the next one, you probably won't notice that, even though you sense it, you won't perceive it because of inattention blindness. Change blindness. Change blindness is it's hard to notice changes between 2 things, especially if there's a distractor in between. It's relatively easy to notice changes if it happens instantaneously. Like, for instance, if I were to just change my shirt right now, it'd be relatively easy to notice the difference because it happens so obviously. But if I were to leave the room and come back and maybe the shirt wasn't from gray to red, it might be a little bit harder to notice. Maybe some of you wouldn't notice. Then thresholds. Thresholds are the smallest amount of a stimulus that you can still detect. So if I'm talking like this, it would be the quietest my voice could get, and you could still hear me. I'm going to turn down my mic. If you can still hear me, I'm talking about different things, and it's the point at which my voice becomes so soft that you can stop hearing what I'm saying. So at some point, it'll get so soft that you won't be able to hear me. And at some point, you start to be able to hear me again, and it's the point at which you can start to hear me again that's the absolute threshold. So the absolute threshold was the point at which my voice got so quiet, it's that volume that you stopped being able to perceive me. Below that point is subliminal. So it was when the voice was still there, but it was so quiet that you couldn't actually perceive it consciously. Supraliminal is anything above the absolute threshold. So my voice right now is supraliminal. It is perceptible. The difference threshold is a subset of absolute threshold. It's an absolute threshold for differences. So that'd be like being able to, if you have 2 glasses of water, both have salt in them, but one has a little bit more salt. How much more salt does the second glass have to have than the first glass for you to notice the difference? Which is similar to just notice the difference. Weber's law, or Weber's law, is that the absolute threshold varies by a percentage or a comparison, not a fixed amount. Or in other words, if you had 15 pounds of weight in your right hand and 14 pounds in your left hand, I would imagine you probably couldn't tell the difference between 15 and 14 because it's very similar. Maybe you could, maybe you couldn't, I don't know. But if you had 2 pounds in your right hand and 1 pound in your left hand, you definitely could tell the difference there because 2 pounds is twice as much as 1 pound. So that's Weber's law. Even though both of those cases had a 1 pound difference, the same fixed amount of difference, Weber's law says that since one is a larger ratio compared to the other, then that's what makes the difference. Signal detection theory is that thresholds can be in different places depending on context. So there are some words that you can say in some situations that have lower thresholds. Like your name has a lower absolute threshold. If your teacher is saying something really boring during a lecture and you're starting to zone out, but then they say your name at the exact same volume as the rest of the lecture, that's going to pique your interest a lot more than the boring stuff they were talking about. So that's signal detection theory. Also, swear words would have a lower threshold. Things like fire, bomb, dramatic words all have different thresholds. Priming is the way advertisements work a lot of time. It's like subliminal persuasion, but a lot less dramatic. A billboard for Dr. Pepper on the highway will prime you later to buy Dr. Pepper. So a billboard is not going to overwhelm you with the compulsion to buy Dr. Pepper, but next time you're in the supermarket, it will make you more likely to buy Dr. Pepper given a choice of Dr. Pepper, Coke, and Pepsi. Sensory adaptation. Once there's constant stimulus, your brain tends to filter out constant stimulus. So that's if there's a hum coming from something, or a smell. If there's a bad smell that is being constantly given to you, your brain will filter that out. Like if you're driving to Colorado and you're going through some of those cow towns, it smells like cow poop for a while until a few minutes in, and then you still smell it, but you don't perceive it. So for the ear, usually I draw my terrible drawing on the board, but we have better than that. We have an actual picture of an ear here. So let's go over the anatomy of an ear. This is a organ of sensation, so that's why we talk about it. Here is the pinna. That's the outer part of your ear right here. It does nothing to actually hear other than to funnel sound into the auditory canal. This piece here, which just funnels sound into your ear. They call this the tympanic membrane. We're going to call it the eardrum, but either works. These 3 bones here are called the middle ear bones. We just call them the middle ear bones, but you might have also heard them called the malleus incus and stapes or the hammer, anvil, and stirrup, but you just have to worry about middle ear bones. By the way, this whole outer part is called the outer ear. This middle part is called the middle ear, and you guessed it, this part here is called the inner ear. This snail-looking thing here, the curled up snail, is called the cochlea. Inside the cochlea, there are hair cells lining the entire inside of the cochlea, and once the eardrum vibrates because of vibrations in airwaves, it vibrates these 3 middle ear bones, and then this little piece here called the oval window also vibrates back and forth, and that jostles fluid inside of the cochlea, which then bends the hair cells. And when the hair cells bend, it sends an electrical signal through the auditory nerve, which is this guy, to the auditory cortex of your brain. And that's how you hear. On top of the cochlea is semicircular canals, or vestibular canals, which controls your vestibular sense. And that is your sense of kind of where you are in space. Right now, the fluid in my semicircular canals are even, which means I'm upright. My brain knows I'm upright. If I tilt, the fluid stays even, but relative to my head, it is not even. So that tells my body and my vestibular sense that I'm tilted a little bit. Also, it's why if you spin around in circles, you get dizzy because the fluid here jostles around. And then the eustachian tube connects your ear, your middle ear, to your throat. Also why when you're up high altitude you have to swallow, which reopens your eustachian tube to equalize the pressure, because this is a sealed chamber, and so the air pressure stays the same here, but if the outside world changes, then you have to equalize the pressure in your inner ear. Sound waves themselves, the process of moving sound waves into auditory perception is called audition. The number of all sound is just number of, it's just compressed airwaves. So when I'm talking right now, my vocal cords are just vibrating, and that's making vibrations in airwaves. And the number of vibrations per second is frequency. That's just the number of vibrations per second. And then our perception of frequency is pitch. If I talk in a higher voice like this, and that has a higher pitch, that means the air is vibrating more often per second. And if I talk in a lower pitch, then that means literally the compressions I'm creating have a lower vibration back and forth. The loudness that I'm talking is physically making the vibrations bigger. That's amplitude, and that's measured in decibels, or our perception of that is just loudness. But decibels is the actual measure on a logarithmic scale of how loud a sound is. There are two ways you can have hearing loss, and that is conduction hearing loss and sensory neural hearing loss. Conduction hearing loss is a mechanical problem with the ear. It is a burst eardrum, a problem with the three middle ear bones, something like that. And that is usually fixed with a hearing aid. So you have a hearing aid which sort of amplifies sounds, and then that's fixed for the most part, a little oversimplified. The other way you can have a problem is with sensory neural hearing loss, and that is a neuronal problem with the ear, usually in the inner ear, a problem with the nerve, or even your brain, but usually the hair cells within the cochlea. And with that, you can have what's called a cochlear implant. And a cochlear implant is this little device right here. And what it does is it's a listening disc that's on the side of your head. That's like a microphone here. And then that feeds the information that the microphone picks up through these wires. And then those wires literally go through your head, and there are wires that are fed in through your cochlea, and they serve as a replacement for the hair cells. So instead of, when you hear a certain pitch of sound, a hair cell moving, that system doesn't work for you. So it's that electrical cable that sends a replacement signal based on what the microphone heard, and then your brain hears in a similar way. There are two theories of sound perception, and they are place theory and frequency theory. Place theory says that it is the location of where the hair cell is located within the cochlea which determines pitch, meaning hair cells in the outer part of the cochlea predominantly determine low frequency sounds, and hair cells in the inner part of the cochlea are mostly with high frequency sounds. That's place theory. Frequency theory is the frequency that the hair cells vibrate, which determines pitch. So regardless of where a hair cell is located, if the hair cell moves very quickly, then it perceives a higher pitch sound, and if it moves more slowly, it perceives a lower pitch sound. In reality, it's a combination of both. It is both where it is located and what the frequency at which it fires that determines pitch. This gross little picture here is with the olfactory sense, which is your sense of smell. Olfactory receptors, you have an olfactory bulb which is above your nasal cavities, and that is the organ that deals with smell. On the olfactory bulb is olfactory receptor cells, which are these things down here, the little yellow in this picture things. They, whenever there are particles in the air, it grabs onto those particles and senses what they are, and then based on what they are and what they are chemically like, you perceive smell. And then the olfactory nerve sends those signals to your brain, and that's how you perceive smell. There are 5 categories of taste, 4 that you know of and 1 that's weird, and that is sweet, sour, salty, bitter, and umami. Umami is the most recent one, and it is a meaty, proteiny flavor. Sensory interaction is that all of your senses kind of play together in interaction. And so it is, if they say that if you smell plays a lot into taste, and so if you were to plug your nose and eat an onion or a potato or an apple, theoretically. I haven't actually tried it. I'm kind of skeptical, but I've heard that they all should taste the same if you plug your nose. The gestalt principles. Gestalt's a really weird field of psychology which deals with perception. And there are several of the gestalt principles. Figure ground perception, as we can see with these images, is whenever you're looking at an object, the object you're looking at becomes the figure and the rest becomes the ground. If you're concentrating on me right now, I'm the figure and my background is the ground. Here, if you're looking at this white, that means the vase is the figure and the faces are the ground. Unless it's the opposite, then the opposite would be true. There are a few organizational principles. Similarity and proximity are two of them. And this right here would be an example of proximity, and that is we group together objects that are close together. So in this case, you see one large grouping of dots and 3 smaller column grouping of dots. And the reason we see it that way is because they're literally clustered together that way, because of their distance they are to each other. This picture here would be an example of similarity. So the reason we see this as rows instead of columns is because our mind groups together these similar looking dots together, which would be the black dots we see as a group of rows, and then the white dots as a grouping as well. Closure in these pictures is our brain likes to close off incomplete objects. So here we see, despite there is no triangle, but we see this triangle here because our brain closes off this incomplete object. We see a soccer ball here in the top right, even though there is no soccer ball, and so on. Or a square here, even though there is no square, our brain closes off incomplete objects, and that's closure. Continuity is one of the more obscure ones. It is, in this picture here, our brain would prefer to perceive lines in, this is kind of a mashup of similarity and continuity. Our brain, other than the colors, would like to perceive this curvy line as one line and then this straight line as one line, but then similarity comes in and we like to group the red together and the gray together. So it's kind of two competing types of gestalt perceptual tendencies there. I made this little worksheet a while ago on depth cues. So the next section is depth cues, and they are the ways that we can tell things are in front or behind based on 2 categories of cues. And the 2 categories of cues are binocular cues or monocular cues. Binocular cues require 2 eyes to work. So if it's the ones that stop working when you close one of your eyes. And to my knowledge, there's only one of those, and it's retinal disparity that you can see here. Whenever an object is really close to you, if you're looking at it with both eyes, your eyes have to cross. So it's your 2 eyeballs literally have to converge on the object in order to know that it's close to your face. And as it gets farther and farther away, your 2 eyeballs become more parallel, non-converging. And that's retinal disparity. Monocular cues only require 1 eye to work. So you can still tell that some objects are in front of other objects based on monocular cues. One of them, you can tell that my left hand is in front of my right hand because my left hand, you can see all of my left hand in this case, and you can only see part of my right hand. That's interposition. So the object in front obscures the vision of the object behind it. Interposition. Another one would be relative size. So this person A here, you can tell the person A is in front and person B is behind, probably, because person A is literally larger in your perceptual field than B, which we perceive as person A is in front of person B. Last one on this worksheet is linear perspective, which is when there's 2 lines, when the lines converge and get closer to each other, we perceive that as getting farther away. So this railroad track here, when the lines are farthest away from each other, we perceive that as being close to us, and as the lines get farther away into the distance, they get closer to each other, and we perceive this as being depth. Relative height's also a little bit obscure, but it is we perceive things to be farther away that are higher up in our visual field, closer to the horizon. But this tree, they're both the same tree, but this tree we perceive as being closer to us, and this tree we perceive as being farther away because this tree is literally higher up in the visual field. Same thing here, we perceive this duck, this black duck, which is the lowest in the picture, we perceive that to be the closest to us, and these 2 ducks we perceive to be farther away. This duck is closer, this duck is farther, and then this house is farther, and that house is even farther. Because as they get higher up in the visual field, we perceive it as depth. Relative motion. So I always love using this video here as relative motion. It's from the Nintendo game Punch-Out. But you can see as Mike is training for his next boxing match, you can see the sidewalk here is moving very quickly past the visual field, and the poles are moving more slowly, the water is moving even more slowly, and these buildings here are moving the slowest past the visual field, and that lets us perceive depth as well. The objects that are moving very quickly past our visual field we perceive as being closer, and the buildings which are moving very slowly past the visual field we perceive as being farther away. The 5 phenomenon is we perceive motion based on non-moving images. In fact, in real life right now, I am actually moving. But when you're watching this video, I'm not moving at all. The video you're watching is either being played at 30 or 60 frames per second, and as my hand is moving back and forth, it's just still images that you're seeing, but you perceive motion. But on this image, you perceive that this yellow dot is moving, even though obviously it's not. It's just being flashed in quick succession, so you perceive it's moving counterclockwise. But in reality, it's just a bunch of still images put together. That's the 5 phenomenon. Perceptual and color constancy is we don't, despite things constantly getting smaller and bigger, you don't think I'm actually shrinking and growing. You know that I am staying the same size. I'm just getting farther or closer to you, or to the camera in this case. That's perceptual constancy. Color constancy is if I were to turn the lights off or on, that would literally, it doesn't really work here, but that would literally change the colors in a room that you were in, but you wouldn't actually think the colors had changed. You would realize that the some context had changed, which changed the colors, but the fundamental colors of objects did not change. Next up, we talk about the eyeball, which is another organ of sensation. I'm using this image, but there's several things on here that we don't need to learn about. We're only going to learn about what I talk about. But on the eyeball, there's some things you need to know. The cornea is the outer layer of tissue in the eye. It doesn't actually do anything for the eye in terms of light. It's more of a protective outer layer, protecting the important stuff inside the eyeball. Then the iris is the colored muscle of your eye. That's the part that's blue or green and looks pretty. So that's this muscle here on the outer part of the eye. On the inside of the iris is the pupil. Pupil is a hole in your eye. It's the black center part of your eye that lets light into the eye. All of this is focused by the lens, which focuses light, moves in and out to focus light on the back of the eye, which is the retina. The retina is the entire layer of cells in the back of the eye. The retina is made up of 2 types of cells called rods and cones. You can see here there are 3 different kinds of cones. One that does predominantly low wavelength light, one that's medium wavelength light, and one that's short wavelength light, long, medium, and short. And we'll talk about how that works later. The rods deal with predominantly black and white, so they don't do color at all. There's a few differences between rods and cones. One, cones do color, as I said. Cones also work best in bright light. Rods do not work in bright light. And rods can work in dim light, cones cannot. And they're both in the center of vision and the peripheral vision, but predominantly cones are mostly centered in your center of vision, and rods are in your peripheral vision, more concentrated. Once the information is picked up by the rods and cones, it then goes to 2 other kinds of cells called bipolar cells and ganglion cells. Once it is filtered through those other 2 kinds of cells, it goes, all that other information is relayed through the blind spot here, which is where you are missing part of your retina, and it exits the eye there and goes to it creates the optic nerve and then goes to your occipital lobe where you perceive vision. The fovea is the center of the retina. It's where they say visual acuity is greatest. It just means you can see better in the very center of vision, as opposed to your peripheral where you can still see, but it's maybe a little bit blurry, harder to make out details. It's part of because in your fovea, in the center of vision, you literally have a higher density of rods and cones, as well as each rod and cone gets its own bipolar and ganglion cell, as opposed to in the peripheral vision, rods and cones have to share a lot of bipolar and ganglion cells. It's, to use a computer metaphor, it's like compression with image formats. The things that you see in the fovea are uncompressed pure visual information, and in your peripheral vision, it's like compressed data. You lose a little bit. There are two theories of color vision, how we perceive color. They both have to do with the cones that we have. One is the trichromatic theory of color vision. That works, it says there are three types of cones: short, medium, and long wavelength light. And the entire visual spectrum of light that we can see, which by the way is a very small subset of all light waves. So these are all of the light waves that exist, and then this little piece here is what we can actually see. Of the light waves that we can see, this range is picked up by the short wavelength cones, this one by the medium wavelength cones, and this by the large wavelength cones. When we perceive the color, let's say orange here, it is primarily the longer wavelength cones which are able to perceive that. So it is the longest wavelength cone which is firing the most, then the medium is firing a fair amount as well, and the short is hardly firing at all. It's the ratio of those three cones and their firing which allows us to perceive the color that we see. It's the ratio of cones firing which allows us to perceive color. The other theory of color vision is called the opponent process theory of color vision. It talks about similar things, but it perceives these cells as working in opposite pairs. So it says there are three opposite pairs that work. One is from white to black, one is from red to green, and one is from yellow to blue. This allows us to explain after images. So if we were to look at, say, the color yellow, and then stop looking at the color yellow, we would stop seeing the color yellow. That makes sense. But the funny thing is, if we look at yellow for a really long time and just keep looking at yellow, we will fatigue our cones, and it will actually overshoot yellow, and it will go to the opposite side, and we will perceive blue for a little bit. To explain how after images work, look at the black dot in the middle. Only look at the black dot and keep looking at the black dot. Here in a minute, the castle, this weird colored castle, is going to change to black and white. I promise there will be zero color in this castle. It will be only black and white. That's black and white. Except you perceive it as being colored because you fatigued all of your cones and they then perceive the opposite color. And that is sensation of perception. So go ahead and fill out the Google form that came with this, and I'll see you next time when we'll talk about learning.